All right, here we go. This is 2019's exam. This is the first question, so this is last year. We'll see if we can mow through this. This is a long one. It's supposed to take us 20 minutes. We got 14 and 50 seconds left, so here we go. Gives us compound urea. By the way, national average on this thing was 5.5. My class last year scored better, a little bit better than that, but not enough better. So here we go. The compound urea is widely used in chemical fertilizer to give us the formula. The complete Lewis dot structure is shown. Identify the hybridization of the valence orbitals of the carbon atom in the urea. If we look at carbon here, carbon has how many domains? It has 3 things that it's bonded to and no lone pairs. And so that hybridization there is sp2. Start the test with a free point, right? Count domains, it's sp2 hybridization, and we are in good shape there. That's it, right? Always 1 for the S's, P's can go up to 3, and then D's after that if you got 5 or 6 domains. Urea has a high solubility in water due to in part to its ability to form hydrogen bonds. A urea molecule and 4 water molecules are represented in the box below. Draw 1 dashed line to indicate the possible location of a hydrogen bond between water and the urea. Hydrogen bond is between hydrogen on one molecule and nitrogen, oxygen, or fluorine on the next molecule. And so this to me is the most obvious looking one. That oxygen to that hydrogen is fine. You get your point there. But you could also do this one. That oxygen to that hydrogen would be fine. This one would be really tough to try to sort out. It's even hard to put. It says a dashed line. It's hard to put dashes in between those two, but technically those two would work okay. I did this one. I thought that was the easiest one. Gave you the most space. You could put a little dashed line. Look at, make sure it's a dashed line to indicate the thing. Draw 1 dashed line. That means you can't take and do this over and over again to that thing. Don't get all crazy, right? 1 dashed line. It just looks like that. Good. Hopefully no questions on that. And we're up to 2 points, and we haven't really done much of anything yet. Perfect. Then it says the dissolution of urea is represented by the equation above. I just cut the equation off. Come on, origami, don't fail me now. Channel my calculus teacher. All right, so they give us an equation here right at the top. It's just a dissolution, just dissolving. 5.39 grams of it dissolved in 5 milliliters of water to make a saturated solution. Calculate the concentration in moles per liter. We have the milliliters, so we can turn into liters. We just have to turn grams into moles here on part C. They give us 2 points for this ridiculousness. These are free points, man. We should be up to 4 before we bat an eye. So 5.39 grams of urea. I'm not writing out that whole formula. 5.39 grams of urea, grams to moles. They didn't even make us add up the molar mass. It's sitting right there for us, 60.06. They give me the molar mass, I'll go to hundredths place. And that's going to give me the moles of the urea. I got 0.0897, I believe, moles of urea. You get a point for the number of moles, just like that. And then you divide that thing by the volume in liters. They gave us 5 milliliters, so we just divide it in liters, 0.005. Everybody here should be able to do that milliliter liter conversion in their head. And we get a big old concentration of urea, 17.9 molar. You get a second point there. And so we're up to 4 points through part C. Sip of coffee and on to part D. Here we go. The student also determines that the concentration of urea in a saturated solution is 19.8. Based off this information, is the dissolution of urea exo or endothermic? Justify your answer in terms of Le Chatelier's principle. What changed here from this saturated solution to this saturated solution was the temperature increased. here, sorry I wasn't pointing at it, from 20 degrees Celsius to 25 degrees Celsius, and it causes a different amount of solute to be dissolved. And so I wrote up my little equation this way on D. I put urea solid going to urea aqueous. So I wrote my little equation like that. What we found is a greater number of moles, or greater amount dissolved, is what they said, right? Because we have a greater concentration, we had to have greater numbers of moles dissolved. And so how did we force the equilibrium that way with an increase in temperature? That delta H had to be over here. An increase in that delta H here caused a shift towards products, to make more products. How do you say that? This is no justification. I did it in my, so I could then have something to look at. But what I put is adding heat stresses the equilibrium. That's what Le Chatelier's principle is about. Toward products so the dissolution must be, the heat was on the reactant side, it must be endothermic. Additional heat stresses the equilibrium towards products, so the dissolution must be endothermic. That's it on D. It's 1 point on D. That would get us up to 5 points so far. Then part E. E gives us this lovely grouping of stuff. It says the equipment shown above is provided so the student can determine the value of molar heat of solution for urea. Knowing the specific heat for the solution is this, list the specific measurements that are required to be made during the experiment. So we want to figure out molar heat. We're trying to figure out delta H of this reaction. It gives us a specific heat constant, which means we are battling from this thing. Q equals MC delta T. Right? So we need a change in temperature. They gave us the constant. We need the mass. The mass of what? The mass of whatever the constant says. And so the constant here is the heat of solution. That's the specific heat of solution, which means we need the mass of the whole solution. So here, what do we need? We need the mass of the urea that we're putting in. We need the mass of the water that we're putting in, because that's what makes up the total mass of the solution. And then we need the change in temperature. So we need a final temperature and an initial temperature reading. And so it just says to list them. It says list the specific measurements. Our measurements are mass of urea and water, and initial and final temperature. Unbelievable. They give you 2 points. They give you a point for having the mass of urea and the mass of water. That's 1 point. And then a point for initial and final temperature. That's your second point. But it stems from that equation. Write the equation out if that helps you, so you know exactly where you're going with that thing. Part F says the entropy change for the dissolution of urea is 70.1. Using that information in the table above, calculate the absolute molar entropy of the aqueous urea. So we just want the aqueous urea. We're looking for the question mark here. They gave us a delta S for the whole solution. They gave us the delta S for the individual solid. We need the aqueous one. Delta S is, if you're solving for them, delta S in this case for the solution. This is always products minus reactants. So this is the delta S of the product That's the aqueous thing minus the delta S of the reactant. That's the solid thing. And then we're plugging in values. They gave us the delta S of the solution, 70.1 joules. So we got 70.1, this is joules per mole times Kelvin. Make sure if you're doing delta G equals delta H minus T delta S, you are aware of that being joules, because you're going to have to convert it to kilojoules. This one we don't, because they're all in joules. Delta S of the product, the aqueous thing, that is what we are looking for. And then the delta S of the solid is 104.6. So we have delta S for our aqueous thing minus the 104.6 joules per mole times Kelvin. That guy added to that guy gives us that delta S of the aqueous solution is 174.7 joules over moles times Kelvin. At least I think. That's my mental math. That's it on F. Winner on F. F's worth 1 point. We got a couple little things to go here. Part G. I just lost my question somewhere. Where'd you go, question? Oh, there it is. Part G says, using particle level reasoning, this is another one we should be able to get, explain why delta S for the solution is positive for the dissolution of the urea in water. Why is it an increase? All they're asking, why is it an increase in entropy going from solid to aqueous? Delta S for the solution is positive because the aqueous particles are more random than the solid particles. Increase in disorder. That's how I'd write it. Randomness, disorder, that's what delta S is. There's what she looks like. And then part H, I got 1.5 minutes. Says the student claims that the delta S for the process contributes to the thermodynamic favorability of the dissolution, and ask you to explain why that is. This is back to thermodynamic favorability is all about delta G equals delta H minus T delta S, where delta G being negative makes it spontaneous or thermodynamically favorable. So I wrote down a positive delta S causes the delta G to become smaller and the more negative the delta G, the more thermodynamically favorable. I would put the delta G equals delta H minus T delta S as part of my explanation there. And there's the rest of it. Oh yeah, we finished with 30 seconds. Shoot. That's what I'm talking about. Let's go! See you soon.